speaker is Clement Suavet, Persistence and Origin of the Lunar Dynamo. Good. Did I say that right? Excellent.
Yes.
Okay. Can we get your camera started?
Can you hear me?
I can hear you. I can't see you yet.
Oh, okay. 1 second. Okay.
There we go. Great.
So,
thank you.
Hi, everyone. So my name is Clement Suavet. I'm a postdoc at MIT in Dan Weiss Polymagnetism Laboratory. So my postdoc is funded by the Brown MIT Lunar Science Institute. So I'm going to present to you the implications of our recent polymagnetic studies results on the lunar dynamo. So for the last few years, we've been trying to reconstruct the magnetic history of the moon by studying samples of different ages. And the reason why we're interested to do that is because the existence of a global magnetic field on a planetary body implies that the body is differentiated and that there is a liquid core. So in the recent years, new evidence for the existence of a lunar core has been uncovered with laser ranging experiments and reanalysis of seismic data showing that the moon has a core. So the moon currently does not have a global magnetic field, but the existence of crustal magnetism indicates that the moon may have had a dynamo in the past. However, 20 years of paleo-magnetic studies of return samples could not demonstrate unambiguously that such a dynamo existed. So this figure represents the paleo intensities of all the samples that have been studied during and after the Apollo era. So there seems to be a spike in intensity between 3.9 and 3.6 billion years ago, which raises the question, why would the start of the dynamo be delayed? Another problem with this data is that some samples seem to have recorded very high fields, up to twice the Earth's current surface field. And finally, the young samples that are much too young to have been around while the dynamo was still active have recorded pretty high paleo intensities. So all this criticism led to investigate other potential origins for lunar magnetism. Impacts are known to generate strong fields and to amplify existing fields. And magnetic anomalies have been identified at the antipodes of major impact basins. So if the lunar magnetism is in fact related to impact, this would mean that we cannot know anything about the internal structure and history of the moon. So in the recent years, with the advancement of our understanding of rock magnetism and the availability of new analytical methods and technological progress have allowed us to revisit lunar paleo-magnetism. So Mike Fuller and Ben Weiss, with a critical review of the literature, have identified the samples that are most likely to provide good records of ancient lunar fields. And in particular, we are now able to select samples for which we can exclude impact as a potential source of magnetism by working on slowly cooled samples that cannot have recorded the transient fields that are generated during impacts. So the first sample that was studied within this framework was Troctolite 76535. So the authors have shown that this sample recorded a stable field on the moon 4.2 billion years ago. And the second sample was Maribazar's 10020. So it appears that the moon had a core dynamo at least between 4.2 and 3.7 billion years. And this is a problem because thermal convection is only expected to be able to power a dynamo until about 4.1 billion years ago. Another model with the overturn of an initially stratified mantle can delay the start of the dynamo, but neither model can really explain the paleo-magnetic record that we have. So this has led people to investigate whether the lunar dynamo could in fact be generated by another mechanism. So mechanical stirring by differential rotation of the mantle and the core could power a dynamo. In one model, this differential rotation is related with the precession of the mantle, and such a dynamo is expected to last until between 3 and 2 billion years ago. In the second model, the differential rotation is generated by impacts. So such a dynamo would only last for a few thousands of years, which would require a series of impacts to to sustain a dynamo for extended periods of time. And basin-forming impacts deliver enough energy to generate such a dynamo, but it's not clear whether this impact dynamo could have been generated by impacts that are younger than the last basin-forming impact that formed Oriental. So by working on samples that are younger, we could potentially distinguish between these two models. So we've decided to work to study high potassium Mare dissolves. So these Apollo 11 samples were formed on the Moon 3.6 billion years ago. And interestingly, they had been studied during the Apollo era, but people did not agree about the significance of their magnetic record. Some authors argued that the dynamo was still active when those rocks formed, based on the very high paleo intensity that some samples had. But other authors rejected these high paleo intensities and said that the magnetic record that was measured was in fact due to contamination by artificial fields. So we conducted, using modern methods, paleomagnetic study of two high potassium Mare dissolves, 10017 and 10049. So I'm not going to enter into the details of the paleomagnetism. So if you're interested, you can take a look at our recent paper in PNAS. So just in a quick summary, we've shown that both of these samples carry a stable magnetization that was recorded while they cooled on the Moon 3.6 billion years ago. So on this figure, you can see the magnetization direction, and the red symbols corresponds to a magnetization of multiple mutually oriented subsamples. So you see that the direction is very consistent between all these subsamples. The intensity of the magnetic field that we found is remarkably similar with that of older samples. So this shows that the lunar dynamo was still active 3.6 billion years ago. We then tried to determine whether it is possible that that an impact dynamo could have caused these strong fields at this time in lunar history. So we went back and used the impact dynamo model. So this model is critically depends on the Earth-Moon separation. So we combined it with orbital models to deduce the minimum impact energy that is required to generate an impact dynamo. And by combining this with the cratering models, we determined the minimum crater diameter sufficient to generate an impact dynamo. And using the impact geometry distribution, we then calculated the probability that a crater with a given diameter was formed by an impact that delivers enough energy to generate such an impact dynamo. So using the crater catalog of the Jim Head and co-authors, we identified the largest crater that was contemporary with the formation of these rocks. So it's a 200-kilometer diameter Humboldt crater. And with our model, we found that the probability that this impact delivered enough energy to generate a dynamo is only about 6%. So it seems to be very unlikely that the magnetic field that our samples recorded was due to an impact dynamo. So I want to make it clear that we're not saying that impact dynamo could not have happened on the Moon. In fact, if you look at the early Imbrian, there's quite a few craters that had a significant probability to have generated such an impact dynamo, such as Schrödinger. So in conclusion, we've shown that the only dynamo model that can explain our paleomagnetic data is the precession dynamo. If that is the case, this would mean that the Moon is the first planetary body for which we demonstrate that a mechanical dynamo occurs. However, we are still lacking models for thermochemical convection with crystallization of the lunar core, and this process might also be able to explain the persistence of the dynamo until late in lunar history. Thank you all for your attention.
Thank you. Okay, great. Do we have any questions for Clement? Okay. So your dynamo is active until 3.6 billion years, but what happens after that? When does the decline actually happen?
So in our lab, Sonia Tiku has been working on samples that are 3.2 billion years old, and so we just submitted a paper about this, and so she found out that the dynamo had already declined while these samples were found on the moon, which means that the decline happened sometime between 3.6 and 3.2 billion years ago. And putting better constraints on when this decline happened will actually help put more constraints on the orbital history of the moon, because it's very poorly constrained at the time. We don't, the history of the Earth-Moon separation is very poorly constrained. So thermomagnetism can help with putting constraints on those.
Okay, good. Well, I'm a little surprised that there isn't more discussion going on about this, because I know several of the people that I see that are online right now have a lot to say. So you guys, don't let this hold you back just because we're trying to do it in the chat box. Please carry on and have this conversation. All of this gets recorded, and so this could be useful at some later point. I encourage you to talk to Clement in the chat box. Thank you very much for that wonderful talk, and we're going to now